So we're going to start by saying our eyes measure wavelength as color. So when I look at a particular color of light, I can see that that light is green or that light is red. If you can imagine like a neon sign, that's what we're talking about. We're talking about a glass tube full of gas, and you can see the color that's coming from that tube. But also, if you were to look through a telescope, you might be able to see a celestial body, something that's out there in the universe, and you can see what color that thing emits. Maybe it's red, maybe it's purple, okay? We can measure that wavelength with our eyes. Then we can use C equals frequency times wavelength to change the wavelength into a frequency. We can do that with math. And then with math again, we can take that frequency and turn it into an energy. So from these equations, we can calculate the energy of the wavelengths of the lights that we see. So again, remember how that works is 1, we see the color. And then 2, we turn it into a frequency. And then 3, we plug that frequency into Planck's equation. And 4, we end up determining the energy. This is some pretty fancy math you guys just learned. Congratulations on that. This is the math that Einstein explains and helps us to understand how atoms work. So light is said to have a dual nature. That means that light sometimes acts like a wave, and light sometimes acts like a straight line particle, like a baseball or an ocean wave. And so light's behavior is sometimes a little bit like each of these things. The baseball idea, light traveling like a particle through space, that one was a little bit crazy. And so of course, with crazy comes Einstein, right? If you want to talk about out of the box thinking, big thinking, we often find Einstein to be a part of that conversation. And so what Einstein says is, yes, waves are traveling like little bits of light, little waves of light from the sun to the earth. But if you back out of that picture far enough, the line from the sun to the earth really starts to act like a little bit more like a single particle. So what Einstein proposes is that when an object gets hot, it emits energy in specific bundles called quanta, kind of like a penny, right? Money is at its essence down to the penny. And these quanta of energy is the minimum amount of energy that a particular atom can lose or gain. So we can only work in quanta, no half of a quanta, okay? So that's the first part. The second part of Einstein's concept is that the photon is like a small zero mass particle that carries this energy to the earth. So I have a picture of what this looks like in my head. And now this is by no means to scale, and it is definitely not what a quantum physicist would tell you. But for my biology mind, understanding chemistry, and working in a first-year chemistry standpoint, this is a great way to picture how Einstein is explaining how light is created. So let's take a look. We're going to start by understanding that this is the sun. Of course it's the sun, right? It looks like a sun. Okay, this is the sun. And way far away from the sun, we have you and me sitting on the earth. That's you and me. We're sitting on the earth. And the sun is going to send light to the earth. That's a really long way to go. If we zoom in and zoom in and zoom in on this wavelength of light, we're not going to see a straight line though. We are going to see a wave. And traveling along this wave are these little photons of energy. Yes, in my drawing, a photon looks like a little truck. And these photons each carry a quantum of energy with them. And they travel along the wave to the earth. But there's not just one photon or quantum of energy. These wavelengths of light are like superhighways full of different trucks traveling along the wave on their way to Earth. So, just for the sake of clarity, my little blue truck is a photon of light, and it carries a quantum of energy as it travels along its electromagnetic radiation wave. And we know that these are waves if we get close enough to them. But from the distance, from the sun to the Earth, we are so far away, it is such a far distance, that the fact that these are waves kind of becomes insignificant. And so along the way, we know that technically this is a wave if we zoom in close enough. But from the distance that we are, in fact, it is traveling like a straight line particle. Whether or not you consider light a wave or a straight line particle depends on where you're sitting. If you're right up here with it, right in the wave, then you have to consider the fact that it is traveling like a wave. But if you're a physicist or an astrophysicist and you're studying how light is moving from great distances all the way to you, in that case, you can consider light a little bit more like a straight line particle. And so what Einstein does is he gives us this way to talk about light where we're not putting light in a specific box. Is it a wave or is it a straight line particle? Well, yes, it is both. It acts like both on different days and under different circumstances. And that's an important thing to consider about the natural world. Remember, we are just discovering it. We're not inventing light. We're discovering light. And so light may not fit into the terminology boxes that you and I already have. And we have to be open to new interpretations of light as being both a straight line and a wave. How does it work? Well, we just don't fully understand light yet. We're still trying. We're still working on it. And so with Einstein, we kind of wrap up our discussion on light. Although this feels like a far distance away from talking about atoms, we're going to use this information and apply it in order to understand first Bohr's model of the atom, and then later to understand why Bohr's model wasn't enough, why we had to eventually move beyond Bohr's model or the planetary model of the atom and step into the uncertainty, the cloud that is the quantum model of the atom, and really our focus for the remainder of the chapter.